Hi. In terms of data, at the for MIPS, we have character data, byte data, half word, and full word, which is 32-bit. To move this data to a MIPS processor, we have the byte load uh, byte unsigned, and we have the store byte, okay, and we have as well the load half word and load store word. Let's take an example where we can really clarify these points a little better. So let's keep going here to our example. So here's our example. In this example, what we do here is that we have this in this data section here. We define two variables, var0 and var1, of type word. Okay. Now notice because this is word, it has 4 bytes. This byte, this byte, this byte, and this byte. The address of the this byte is var0 plus 0. The address of the second byte is var0 plus 1. The address of the third byte is var0 plus 2. And the address of the last byte, which is this one here, is var0 plus 3. Similarly, var1 has these bytes, okay? And the address of this byte is var1 plus 0. This byte var1 plus 1, var1 plus 2, and var1 plus 3. Okay. In fact, so for example, this byte here, the address of it is equal var1 plus 1, and I know that var1 itself is var0 plus 4 and plus 1. So you can see that var1 itself is var0 plus 4. In other words, that if I add 4 to this variable, I will get var1. Okay. Now, so here we load the effective address of var0 into the base register S1. How can I load the effective address? Well, loading effective address, actually, that's not a MIPS instruction. That's an instruction that is decomposed into two instructions. You see, the address in MIPS cannot be loaded at once in the register. So what we need to do here is that, so for instance, the address, let's say, for example, the address of var0 equals 1001 0004. That's the address of var0. How can I move this address into register S0? How? Well, we have to do it in two steps. The very first step is that I take this number, is that 1001, and then I move it to the upper part of S0. So let's say, for example, uh, here, so I move it to the upper value of 1001. Okay, so I took this and I move it to the upper value. Then I move the 0004 to the lower value of the register. At the end, the register will have a value of 1001 0004. Somebody might say, why don't we do it in one shot? Answer: we cannot move immediate data which has a width of 16-bit. So we have to do it in two steps. First, as we are saying here, for example, first we move the. Now here he's using. We are moving var into S1. He's using an intermediate register to help me. So I'm moving this to the upper part of the intermediate register, and then what we are doing, we are ORing this immediate OR with this 004 with the register that I have on the upper 10001, and save off the result S1. The result at the end I'll have S1 equals 10010004. That's what I need. I cannot do it in one shot because there is no instruction that can move 32-bit worth of data into a register. This is 32-bit. I have to do it in 2 steps. Whoops. I have to do it in 2 steps. Okay, so now let me just do an erase here. So that I can. Okay, so now I have my pen back. Okay, so this is 2, 1, and 0. Okay, now I'm loading the effective address of var 0 into S1. So when I say load the word at address var 0 plus displacement of 0 to T1, I will load the entire word into T0. So this into T1, sorry. So T1 now will have 0, 1, 2, 3, 4, 5, 6. And this is, by the way, it's a hex. It's a hex number. Okay. Okay. So this is a 32-bit. Now, what about if I instead of displacement of a 0, I add a 1, a displacement of a 1? Well, if displacement of a 1 will make this number or this address, this address here is divisible by 4 because it's a word address. If I add a 1, the address will not be divisible, and therefore I cannot load a word from an address which is not divisible by a 4. So that's why I will get an error misalignment. Okay, so again, let's say, for example, the address var 0 is 100, which is this one here, 100010004. If I add 1, it becomes 0005, which is not a word address. That's why I will get an error of misalignment. Now, how about if I load var1 into S1? Now, var1, which is this one here, which is this one, into S1. Now, then I would like to load from S1, okay, which is this word here, um, displacement of 0. So I will load a byte, which is EF. So EF, I will load it into what register? Into T1. But remember that in EF is a byte and T1 is a register. The register has 4 bytes. The question, when I load a byte into a register, what happens to the other 3 bytes? What happens? We sign extend the byte through the register, meaning I will look at the most significant bit in the byte, which is in this case 1, right, and extend it all the way in this word. So T1 will have a value F F F F F E F because I sign extend. Now, notice here, this is I'm loading this byte. Then now I'm gonna load this byte, and I'm gonna load. Let's see. Interestingly, when I load this byte, which is say T1, which is var1, displacement 3, which means this byte 79, okay, into T1 register. So 79 here, I'm loading T1. Notice that the 7 is 0111, so it has a most significant bit of a 0. So the rest of the bits of the other 3 bytes in the register will be sign extended with 0 because the most significant bit of the byte that I loaded is 0. Now I can state, so here what I did words. Here I'm doing loads of bytes. Let's do loads of half words, meaning half of the. So here I'm gonna do var 0. So S1 now will have var 0. So I'm going to load the upper. I'm going to load half var 0. I'm sorry, here's var 0 with a displacement of 0. So what happened? I will load, so this is the displacement of 0. I will load this half, okay, into T0. Again, the rest of the bit, sign extend. Sign extend. What happened if I add a 1? Well, if I add a 1, I will have misalignment. Why? Because half word, the address must be divisible by 2. If I add 1, the address will not be divisible by 2. How about if I add 2? If I add 2 here, I will pick the other half of the word. So I'll take this one here and load it here. and then the rest of the register of T1 will be sign extend. Why? Because this byte is 0000, and this 0 will sign extend to the rest of the register. Okay, let's now load this 4 plus S1. S1 is what? Var 0. Var 0, var 0 plus 4, var 0 plus 4, which is here, this is the 4. This will give me var 1. Okay, so which means that I'm just loading var 1 into T1. So T1 now, T1 uh, uh, T1 will have a value of 7 9 A A B C D E F. Now what I want to do now, I'm going to store half of the word in T1, which is the lower. Typically we store the lower half, which is C D E F, into S1. Okay, so I'm going to store what, the lower half of the register, which is these two bytes, into, let's change color here. Let's use so into where, into this here. Okay, so now var will be 0 1 2 3. What's the new value? C D E F. CDF. Okay, because and that's what I'm showing here, 0 1 2 3, the var 0 CDF. Now what about if I want to store from T0 the least significant byte, always the least significant byte, which is this one, EF. I want to store it at position 3, so I take the EF and I take it all the way to this position, which is here. This is position 3, and I store EF3. So now you can see EF comes in here at the value of the var 0. This is the effect of the store of the half word. This is the effect of the storing of the byte, because we changed the address of the byte to be position 3. Okay. Okay, so let's go back and see what is left off in this chapter. I think I finished pretty much most of the points here. Okay, so this is the load upper immediate and ORing when we implement the load effective address. Okay. Sorry. Okay, yeah. So that's that. We explained this, and this is when we say that this is the address here, the delta, the delta. When we do branching, so the delta is saved in the instruction. So I compare this is equal to this, and then we move with the delta. Uh, so as for the PC relative addressing, uh, we say that when you have kind of like a program, right, and then you have a jump using branch if equal or branch if not equal, that delta is saved in the instruction. But we don't save this delta here, this delta, which is between the instruction and the target of the branch. This delta is not saved as bytes, it is rather saved as words. To do this, what we do, we divide this delta by 4. Okay, so this offset here, this offset is saved in terms of words, not in terms of bytes. So what we do, we divide it by 4. So to compute the target address, which is this one here, okay, so to compute the target address, which is this one, we multiply offset by 4, because the offset is in words, okay, by 4, and then we add it to the PC. Okay, all right. So in terms of the jump instruction, so let's say for example we are doing jump to some location here. Okay, so let's say this is let's say this location is here, and we can jump anywhere in the memory. this address here, okay, is consists of 32-bit. 32-bit. We know that the least significant two bits are zeros always because it's a word. The next 26 bits are saved in the instruction. The upper four bits are coming from the jumping instruction because the upper four bits of the address of the jumping instruction and the target, they are the same. So this 26 bits has to be saved in the instruction. The two zeros are always there. The four are shared between the jumping instruction and the target instruction, the upper four bit. Okay. Now, so let's take a look here on how to generate the machine code for the branch instruction. Notice here is the exit instruction. Let's see, what's the delta between here and here? Well, count. For this instruction, the branch, the current PC is here, which is kind of funny. You would think that it's in no the current the PC always advances to the next instruction. Okay, so now this is the PC for this instruction. Now, what's the distance between the PC and the exit? One instruction, two instructions. Okay, one, two, right? Or let's just two words. Okay, so now in the encoding of this instruction, the delta is 2 because it's the distance between this PC and the label, which is right here. Well, how about jump if loop? Well, jump if loop, this is the loop address, and we know that this is we're gonna save the least 26 bits, and the upper bits are zeros, so we need to divide this by 4. So we divide this by 4 and we get 2000. Why we divide by 4? Because we convert the byte address into words address. This is the word address. Okay, so we divide by 2. This is the opcode for the jump instruction. Okay, now we don't have branch. See, when we branch if equal, we are limited with the delta to 16-bit. Well, what about if I want to branch to farther distance? Now then I need to use the jump instruction, which gives me absolutely anywhere I want in the memory with the except of the upper 4 bits. They have to be shared with the jumping instruction. In this case, I can compose two branch if not equal with a short delta with the suppose I need to have a far jump that says compare these two, and if they are equal, go to this far address. So what do? I said compare these two, and if they are not equal, go to L2, I'm sorry. Otherwise, go to this jump far to L1. Again, why can't I do this immediately? Because if L1 is far address, does not fit in these delta, I cannot implement it with MIPS. But MIPS provide me two instructions to do it. Okay. Now, um, more in the rest of the chapter in how to convert machine code into I'm sorry, assembly into machine code. So here is a load word, okay, and we need to use the I format. This is the I format, the opcode from the table 23 source RT. Okay, so source and RT, and we plug in these registers, and the 16-bit number, which is 24, comes in here, and then you form this address, this machine code. Okay, another example here, as we have seen before. Oops, sorry, this is flipping quicker than I add immediate. Again, this is I format, opcode, RS and RT. Okay, both are the same, so that's why you see 19. And this is the immediate number, which is 4 right here, and this is the I format. Let's see if I Okay. Another is the add. We have taken an example of add. More examples here. You can look it up yourself, and so I think this is kind of what I want to cover in this chapter. There are more complex subroutines. You can read it in your own, and that concludes the chapter for MIPS instruction. And thank you very much.